Hello, this video is about bond strength and how we can use that to actually calculate the heat of any kind of reaction. So, first we're going to look at bond enthalpy. So if you technically it's defined as the strength of a bond is measured by determining how much energy is required to break that bond. So if you see right here we have two chlorine molecules hooked together. If we want to break them apart into two chlorine atoms, it takes a certain amount of energy. In this case, it takes 242 kilojoules per mole. Anytime you want to break a bond, you have to input energy. That's a positive value. So we can look up for there's a table of the averages. So you can see here on the table on the right that a CH bond is worth 413 kilojoules per mole, so you have to input that much energy in order to break that bond, which is different from the CC bond, which is 348. Now technically you can't have any CH bond in any molecule isn't exactly the same. Like if you look at CH4, the CH bonds in there are actually going to have different average bond energy than the CH with this 3 chlorines around it. But this is looking at average, so it gets pretty good. Something to note is looking at the multiple bonds, things we covered before. If you have a double bond, 2 carbons together, it's 614, which is a high number, kilojoules to break it. But if you have a triple bond, that's even stronger, 839, which makes sense. A triple bond means 3 bonds you've got to break. You're going to need more energy to make that happen. Okay, but what we're trying to look at is if you have a chemical reaction, what is the actual heat of that reaction? And we can find it by doing this formula. That funny looking E thing is the summation, so the summation of all the bond enthalpies of the bonds broken minus the summation of the bond enthalpies of the bonds formed. I'm going to do an example problem on that. But if we find that difference, if you look down at the bottom here, this is like a reaction coordinate diagram. That difference is going to be the heat of the reaction here. This is how much energy it takes to break the bond, this is how much energy it takes to make the bonds, and that difference is going to be the heat of reaction. So I'm going to do this example for you. Okay, right here. Okay, so the first thing that I like to do is draw the molecules. Oops. Here's CH4. And then I got my chlorines, 2 chlorines together. Drawing the Lewis dot structures. On the other side, I've got I'm going to draw these 2 over here. Do it right here, CH3 with 1 chlorine attached, and then an HCl. And what's happening here, if we kind of highlight what's actually going on, is that this chlorine-chlorine bond is breaking, and this CH bond is breaking, and what we're going to be doing is making the CCl and making the HCl. So this chlorine is going to be attached to here, and that hydrogen is then going to be attached to there. So if we think about things, I'm going to break a CH and a ClCl. And then I'm going to make a CCl and an HCl. So what we're going to do is we're going to find the difference between these two, the breaking and the making. So I'm going to use that summation kind of thing, where the heat of the reaction is going to be all the bonds that you break minus all the bonds that you make. Break minus the make. So I'm going to find my breaking would be CH, 413, plus the ClCl, where is he? Here he is, 242. And then the making is going to be CCl, here it is, 328, plus HCl, here he is, 431. Oh, that's a 1. And if I take those 2 numbers and I subtract them, I get a change in H of the reaction to be negative 104 kilojoules. Which means if I actually do this reaction, I will produce 104 kilojoules per mole. That's what the reaction kind of means. So this heat of the reaction would be the heat of the reaction that would go after the equation that we would use like when we do heat in the mole map kind of problems. So there's your crash course on that.